Yeah? Okay, good. So I looked here at the morphisms between two torsion Z modules. Well, actually, I did not make any assumption on N and M, so they might have been 0. But so you see that some, well, by studying these Hom sets in a category, you get some information on the objects. For example, if N and M are relatively prime, then there is only the 0 map between them. This set will then have, the GCD will be then 1, and that means that there will be exactly one map. And that must be the 0 map, because the Hom is an abelian group. And if that has only one element, it's the 0 group. We can also look at free modules, but actually, have we already seen? Yeah, we saw the R to the N in Arno's lecture. So other objects that we automatically have, we can also look at this thing, Hom in Z mod from Z to the N to Z to the M. And, well, actually, here, this is this Z module has a basis, well, let's say E1 up to En, and E1, this is the, let's write them as column vectors, 1 and then zeros, and then this is the 0, and it ends with a 1 there. And this has also a basis, and here you can also describe the morphisms from Z to the N to Z to the M by matrices, and they have to have M rows and N columns. And if I have a matrix here, then what is this morphism? Well, this goes to an element here, say a vector V, goes to A times V, right? You can multiply such a column vector by such a matrix, and you get such a thing there. And those are precisely the morphisms of Z modules. And this actually, for commutative rings, well, let me go. You would think that the same works for arbitrary R modules. If I take any ring R and I take R to Hom from R to the N to R to the M, that I get the same. But I'll tell you that that is not really the case unless R is commutative. So if R is not commutative, you have to set it up a bit differently. So 3 then, for R, just a ring, and I take N and M in natural numbers. I want to understand Hom of R mod, and here I have left modules, right, R mod, R to the N to R to the M. And well, why can't I use the same formula? If I would do the same here, I would have to do this, right? I would have to check that I would have, say, R times V goes to A dot R times V. But that should be the same as R times, this should be R linear, so R times A dot V, right? But you see that when you try to do this in a non-commutative ring, it will not work, because you are going to multiply the coefficients of A on the right by R or on the left by R, and that's not the same. So for arbitrary rings, you have to actually multiply, if the scalars of our, if we have a left module and we multiply our vectors on the left with elements of R for the R module structure, then the morphisms should be, they should commute with them, they should multiply on the right. So here you do the, so you can also take, so let me now, so I say now I switch this, the size of the matrix. Remember, here it is n times m, and there it was m times n. And I'm going to map a matrix A here to a map that multiplies V goes to V times A. But now, of course, and the V should be in R to the n. And R to the n, I identify that with the row vectors. So this is 1 by n matrices with coefficients in R, right? And now I can multiply on the right by a matrix that has n rows. And that is what happens here, right? And now I will have that for every R in R and for every V in Rn, I will have that R times V goes to R times V times A, but this is because I multiply from different sides, that is an associative thing. And so that is so that explains that this map is now linear for left multiplication by elements of R. Right? So still matrices, but beware, for non-commutative rings you have to multiply from the other side. Okay, then we go to the actually a more interesting case, a polynomial ring. So the next example, number 4, is we're going to look at modules over the polynomial ring. So the polynomial ring is, what should I say, right? As a kx is the direct sum I in n k times x to the n. It has a basis as a k vector space consisting of all the powers of x. That should be an I then, right? And the multiplication is x to the I times x to the j. Of course, it's x to the I plus j. That is why it is written like this. And we are interested in modules over this ring. Right, so I will, if I have an element f in here, I will write it as sum fi x to the I in n, and with the condition that only finitely many of these fi's can be non-zero, just like the basis that Arno talked about. Okay, so let us look at these things. What does it mean to have a let M be a kx module? Well, that means that M is an abelian group, and I can. So I have a multiplication. So M is an abelian group, but I also have a multiplication map k times m, kx times m to m, and well, I can restrict this to a map just by taking the constant polynomials in the this kx has a subring k, and I restrict it to that. And here I have a multiplication. I get a multiplication here, and this map gives M the structure of a k vector space. So each kx module is a k vector space, but I know a bit more. I also have one special map from M to M, and we have, also I have the map that multiplies by x from m to m, right? That sends m to x times m. And that is this one commutes. Commutes with the multiplications from elements by k, because this ring kx, so both x and k are in this ring, and this ring is a commutative ring. So that will commute. So this map here, this map is a linear map, is k linear. So I have shown to you that if you start with M, a kx module, kx module, it gives to me M and say x dot is a k-vector space plus an endomorphism, right? K linear endomorphism. And I claim that these are equivalent notions, because if I start with something like this, what can I do? Well, I can say I know how to multiply by x on this. I know how to multiply by constants, because that's the k-vector space structure. And multiplying by x squared is multiplying by x and then again by x, and so on. So I know how to multiply by every element. So f sum fi x to the I times m. I can do it if I know how to multiply by elements fi and by x. Then repeating that I times, say, gives me multiplication by x to the I. You can also say that if I have this, to give a module structure here, I have to give a homomorphism of rings to the end or as a abelian group of M. Well, this on the subring K, I use the vector space structure, and then I just have to say that X goes to the given endomorphism, the endomorphism that is given, and then this, the universal property of a polynomial ring then fixes the rest of this map. So it is that every element is uniquely written like this, so it has, you can uniquely map it to here. Right, so this, yeah, okay, so that is a nice thing. Here we have, well, I have another description of this category, but I have now written the objects, but not yet the morphisms. So I should also write the morphisms that we know that what they are here in terms of this, right? So if I have, now that V and an endomorphism A, so this is a vector space, this is an endomorphism, and W with a B of this type, then what are the morphisms? Well, let me take a new board for that. What are the morphisms between them? When I say each of these gives me, this one gets a structure of a kx module, that has a structure of kx module. What are these morphisms? So hom, oops, in the category of kx module, from, say, V with A to W with B. This, I claim, is the set of F from V to W that are K-linear, and for every V, we must have that F of A times V, A applied to V, is F, first A then F, that is B applied to F of V. Because what does this mean? Because in other notation, this is F of X times V, and this is X times F of V, right? I mean, the way to pass from one side to the other is to make X act as the endomorphism. Right, so actually this I must have, and if this holds for x, it holds for x squared, and so on. So it holds for every polynomial. So that says that these two sets are the same, but I still need to close it. And one way that is nice to write it is to say, well, I need an f here from V to W, that must commute with the A here and the B here, right? This diagram has to commute. And now you also see how you compose things like this. If I have a U with a C, right? You also see that, and I have a G, then you see that if these diagrams commute, then by composing, it also commutes. So it is a nice way to see. It's very useful. We will see that in the next lecture, that this gives you a lot of information on endomorphisms of vector spaces. Okay, well, that's it.